So what were the reflectors doing? Okay, so QR decomposition is something that we are looking at, and the reflectors is something that are of interest to us. Okay, so what were we doing? We were actually looking at the orthogonal matrices, and we were discussing about QR decomposition, right? A is equal to QR, where Q is orthogonal and R is upper triangle, right? And why is this required? This is required because with the help of this Q and R matrices, we can actually introduce zeros in the given matrix, right? So those zeros that are introduced are in the form of R, right? And then we can solve the system of linear equations very nicely, very easily. Okay, so that is what we have. So yesterday we saw that suppose L is the line through which you want to reflect. L is the line through which you want to reflect. Then we took a unit vector on this line L. We took a vector which was orthogonal to this L. I think the symbol that we used were L and U. And then we constructed the matrix P, which was which was U transpose. And then we constructed the matrix Q, which was 1 minus 2p, which is nothing but 1 minus 2 u transpose, right? So this matrix was the reflector matrix. So this matrix actually gave us reflections, right? Then we said that, okay, we can generalize this concept to an n-dimensional vector. So here we did n is equal to 2. And then we said that we can generalize this concept to an n-dimensional space also. So we constructed a space of hyperplane. Okay, so this is the set of all V in Rn such that inner product of U with V is equal to 0. Okay, for a fixed U. Okay, for a fixed U. So I can put that U here, H sub U. Okay, so basically what I am doing is that I am giving you the normal direction U, and once I give you the normal direction U, you are finding out the plane, all the vectors which are orthogonal, to U. That is what I am giving, and this will be an n minus 1 dimensional subspace. This is an n minus 1 dimensional subspace. Okay, so this subspace we generally call as hyperplane. And what are we interested in doing? We are interested in reflecting through this subspace. So it is a generalization of the line. So that is what we are going to do, right? And now this vector u, given vector u. So yesterday we took this vector u to be of norm 1, right? And yesterday there was a discussion about how these vectors v should be. So now you see these vectors can be basis, or I don't even need a basis. I can just define the entire subspace. And this vector u that you see here, we had taken normalized, right? So this u vector was such that norm of u was equal to 1. If the norm of u is not 1, we can normalize this vector u. It doesn't matter. And by normalizing this vector, we can work, right? So instead of u, if u is not normalized, is not a unit vector, or is not a unit vector, normalized vector, then normalize it, right? So how do we normalize it? The way we normalize it, it's okay. So you want I minus 2p, or which is equal to I minus 2 u transpose, right? And if u is a vector which is of norm 1, then this works well for you, right? But if u is a vector which is not norm 1, then this will not work well. This matrix I minus 2p will not be an orthogonal matrix. Then what do? You divide the vector by its norm, right? So if u is not a unit norm vector, what do? Normalize. Correct. So how do we construct q in this case? I minus 2 u by norm u. So this vector u by norm u will have the same direction, but what will be the difference? The difference will be the norm. So this vector will have one unit norm, and u transpose. Correct. This is what we will have. So how does the q look like? I minus 2 divided by norm u square into u transpose. That will be your reflector Q. Okay, so this reflector is the reflector that you will build, and using this reflector, you will be able to reflect through this subspace H of U. Okay, so that is what is happening here. And then, like yesterday,
Yes, sir.
yes.
Sir, why did we normalize the vector u?
The reason for normalizing is that the orthogonality. So for example, you want to check Q, whether Q is orthogonal or not. So Q transpose is its inverse, right? So if you take Q transpose Q, you have I minus UU transpose into I minus UU transpose, right? And if you do not have U to be norm 1, you will not get identity matrix here. The norm of U will be the normalizing factor on the diagonal entries of identity. So in order to make sure that you get identity here, you want U to be unit vector. So you expand this and you see for yourself that this is what is going to happen. So that's why we want unit norm vector there. So in order that we have a unit norm vector, this normalization is required to be. Okay. So you can just expand and you can see for yourself. I transpose minus U transpose transpose. That is what this bracket is. I minus U transpose, and then you can do this. I minus U transpose minus U transpose plus U transpose U transpose. Right? So this will be equal to 1. If norm of U is 1, then this is equal to 1, and then this will cancel with itself, and then you will have I minus UU transpose, right? So did I make a mistake somewhere in calculation? I need identity here, right? I minus UU transpose plus UU transpose. So have I made a mistake somewhere?
Sir, it will be I minus u transpose u.
Yeah, I minus U transpose U. Okay, and then no, you. So you just expand this properly and you will get it. Okay, so this is U transpose into U transpose, right?
Is I
This is
minus
I
2
minus 2 UUT.
yeah. So you just see, and this product where you get in this expansion in these two terms. Now this is important. If this is not norm 1, this will be some scalar that will create trouble for you eventually. Okay, so that's why you need normal. So you expand this and you will do it. I'm not doing it formally. Okay. Uh, So, like yesterday, and like in case of rotators, the question that we want to ask here is that why these reflectors are important for us. So, the reason why these reflectors are important for us is that they can introduce zeros in a vector. Okay, and how do they introduce zeros in a vector? We'll see. So, this theorem is a useful theorem which helps us do it. Okay, so what does the theorem say? So the theorem says that let x and y be any vectors in n-dimensional space Rn with the fact that x is not equal to y and norm of x is equal to norm of y. Okay, so I pick two vectors with equal norm, and then what am I saying? There exists a reflector Q. There exists a reflector Q such that qx is equal to 1. Okay. So what we are saying, if there are two vectors with equal norm, then you can always find a reflector that will reflect vector x to vector y. How does this theorem help us? The way this theorem will help us is the following, right? How does this theorem help us? This theorem help us. So this x is the first column of A. Okay, this vector x is the first column of A. So this is like A11, A21 up to AN1. And this A matrix, I really don't worry about it. What do I want? I want to build a reflector such that this A11 hat and all these zeros are here, right? And this matrix, whatever happens, I am not really concerned. So this vector is my y and this vector is my x. So if I choose this A1 hat, which is equal to norm of this vector x, okay, then I will be able to construct a reflector Q such that all these entries in one shot go to 0. That's how this theorem is really going to help us, right? So this theorem says that you can always build a reflector if the two vectors have same norm. So if I choose this to be equal to norm of x, if I choose this to be equal to norm of x, then my job is done. I'll be able to build a reflector such that all these entries below the diagonal go to 0, right? And then I will need n minus 1 reflectors, because in the next step, what will I focus on? I will focus on only this part, and I'll build a reflector in an n minus 1 dimensional space, strictly speaking, which will take this 2 star and zeros, right? And that's how I'll keep on introducing zeros in the matrix, and with n minus 1 reflectors, I'll be able to build the upper triangular matrix. Okay, so this is how the theorem is going to help us. So let's see the proof. Proof is not really very difficult. Okay. Uh, so we know that we want to find out, we want to compute Q, the reflector, compute Q such that Q is of the form I minus gamma u transpose. Okay, so U is any vector, non-normalized also, so that gamma is basically 2 divided by norm of U square, right? That's this gamma really is. And how do I want to find out Q? So we want to compute Q such that this, what will we need? We need to find out U. Okay, so we need to find out U such that this Q, which is equal to I minus gamma u transpose, is such that Qx, which is nothing but I minus gamma u transpose x, is actually equal to 1, right? So this is what I want to do. So basically, if you see, if you want to find out the reflector, the only thing that you want to compute is this u vector. Somehow from the vectors x and y, if you are able to come up with the vector u, okay, which will be of this particular form, then you would have built the um, reflector completely, right? So what we really do is the following. Okay, so what we are going to do is as follows. So suppose x and y are two vectors, okay, which are of equal norm. Because they are of equal norm, they will look like this. What do I do is I build a line, along the angle bisector. Okay, so this is the angle. I build a line L along the angle bisector. And what am I going to really observe here? Okay, what you really observe here is that x is the reflection, y is the reflection of x, through this line L, right? And now what am I going to do? I am really going to work with the vector algebra that I already know. So from this line, if you construct this vector, do you all agree that it is half of x minus y? And if I look at this vector from here to here, that is half of x plus y. This simple vector algebra, right? Once you know this, your job is done. And now, once you see these things, you already know what is your u and what is your v, right? So what is your u here? What is your u here? This will work like your u and this will work like your v, no? Because you want this u to go down, right? Minus u, that's what should happen. And this v, which is half of x plus y, should remain on the line under the action of q, right? That's how you want to build your q. So that's all I will do. Okay, so want to construct q, we want to construct the reflector such that q of x minus y is actually y minus x. Okay, that is what you expect. And you want the q of v has to be equal to v. So that's another objective, right? So you will want to see this happens. So one thing that you can observe here is that how you can write down this vector x. Okay, so how do you write this vector x? So you can write down this vector x in this particular format. And now what I'm going to do is something really very interesting. Okay, so just to make things clear, I can just write it down as half of x minus 1. Okay, so same thing basically. And now what I'm going to do is the following. Okay, you observe this. So observe x plus y and x minus y are orthogonal to each other. Okay, and you can very easily prove it. Okay, you really don't need to like do this, but okay, I'll just do it for once. So if you expand the inner product, that is what you will get with a negative sign. So this will be with the positive sign, right? So this basically will give you inner product of xx minus inner product of yy, which is nothing but x square minus y square, which is equal to 0. So that means that x plus y is perpendicular to x minus y. Okay, so half of x plus y is perpendicular to half of x minus y. And why is that true? This is true because you started with x and y such that norm of x is equal to norm of y. And what will happen? So now you look at qx. So what will happen to qx now? So you will have qx is equal to half of qx minus y plus half of qx plus y, correct? So that is what you will have. So what is your q here? Here the q is basically I minus gamma u transpose. But what is your u? Your u is basically that vector half of x minus y, right? Where u is equal to half of x minus y. So if you have chosen your u is equal to half of x minus y, then that implies that q into x minus y is basically y minus x, and q of x plus y will be equal to x plus y, correct? That is what you will have. And this implies qx is equal to half of qx minus y plus half of qx plus y. What happens to this? Half of y minus x plus half of x plus y. So you will get this to be equal to y. So q of x you will get equal to y. So you have built a reflector. So this is the reflector that you have built. And how did you build the reflector? The reflector was built with the vector u. You need that vector u. And how do you take that vector u? You take that vector u to be equal to x minus y, half of x minus y, or x minus y. It doesn't matter. Scaled version of x minus y is equal. And once you do that, you have built a reflector, and that reflector will reflect x to y. And now once you do this, then it's very easy introducing zeros using a reflector. So in case of rotators, introducing zeros in a vector using a reflector, correct? So using a reflector, if you want to introduce zeros, what happens? You have x, which is equal to x1, x2 up to xn. And now you want to send this x to a vector y, which looks like y1, 0 and 0, all the zeros, okay? So x and y, they are vectors in Rn. If you wanted to do this operation using rotators, you would require n-1 plane rotators. Do you remember in the case of rotators, we had done this discussion, and you would require n-1 rotators to do this operation. But in case of reflectors, you can achieve this operation within one shot. In one shot, you will be able to construct these zeros. Okay, so how do you do that in one shot? So now you choose y1 to be equal to 2 norm of x. If you choose y1 to be equal to 2 norm of x, then do you agree that norm of x is equal to norm of y? Is that okay? Then norm of x is equal to norm of y. Then use the previous theorem. Use the previous theorem and do what? To construct a reflector Q I minus 2 u transpose, where u is equal to what? Where so this, instead of 2 I will use gamma so that you can do normalizing, where u is equal to x minus 1. Okay. So it's so simple. U is actually equal to x minus 1. And you construct this reflector such that q of x is equal to 1. Means that q into x1 up to xn is actually equal to y1 0 or 0. So you have introduced a 0. And once you are able to introduce the 0, then what do? You apply this repeatedly n minus 1 number of times. So in this QR decomposition, so what do? QR decomposition with reflectors. QR decomposition with reflectors. So what do you do in this QR decomposition with reflectors? You start with a matrix A, which is a matrix of the size R n by n. Okay, so it's a n by n matrix, and you have these columns. So let us say A1, A2 up to AN. Then what do? First, you build a reflector Q1, which takes you to this particular form. Okay, and these entries, these columns are as is, right? Then what do? You look at this second column. Okay, so what is happening in the second column? You have some entry here, you have some entry here, you have some entry here, and so on and so forth. So what do you want to do? You want to convert this vector such that these guys are all 0, right? So this is the guy that you are interested in. So this guy got norm A1, right? So this guy got norm A1. Now what will this guy will get? This guy will get norm is equal to this. So whatever entries are here, that's the norm. Based on that, you will construct the vector. So you'll construct Q2. Okay, but how will this Q2 look like? This Q2 will look like 1 0 0 0 0 0, and this Q2 tilde, where Q2 tilde will act only on this vector. So it will act on this vector. So if I use colors, because I can, so this blue vector which has n minus 1 entries, correct? And by using these n minus 1 entries, what will happen? You will get this vector of this form, star and zeros, right? So you will construct zeros in the second block, and then Q3, now you know you will have two columns of E1 and E2 of identity matrix as it is, and then Q3 tilde here, which is n minus 2 by n minus 2 matrix. So this matrix is n minus 1 by n minus 1. And in this way, you will build how many reflectors? N minus 1 reflectors. So these n minus 1 reflectors, if you apply, this matrix that you get here is eventually R, right? Upper triangular matrix. And with only n minus 1 reflectors, you will be able to construct the QR decomposition. Okay. In case of rotators, you require something of the order of n squared by 2, right? Roughly n squared by 2 number of reflectors were required to construct the R matrix. Here with only n minus 1 reflectors, you construct the R matrix. Okay, so that's how you do QR decomposition with the reflectors. So once you achieve this QR decomposition, the same, like if you want to solve the system of linear equations, solve Ax is equal to B, then if you are not in need of explicit QR decomposition, if you do not want to explicitly compute Q and R matrices, then what will you do? You have this matrix A, then you apply Q1, you apply Q2, so on and so forth, apply Qn minus 1 into X, then you have Q1, then apply Q2, apply Qn minus 1, right? So this is what you do. So this whole sum, his whole product is basically the upper triangular matrix R, right? So you get this upper triangular matrix R with zeros and this star into X is equal to this right hand side if I call it B tilde, right? And again, like yesterday somebody was asking, you will do this multiplication first, then you will do this multiplication and so on and so forth, and then you can save a lot on the computations. And here you solve this system of equations, solve using backward substitution. Solve using backward substitution, and you get this particular. Okay, so this is how you can use QR decomposition to solve the rectangular, sorry, to solve the square system of equations. Is that fine? Do you all agree? Is there any doubt here? Okay, excellent. So if this is clear, then I will just say how QR can be used for rectangular systems. For tall systems or over-determined systems, what is going to happen? AX is equal to B. Okay, so pictorially, how does it look like? It looks like this. Correct? This is A, this is X, this is B. Correct? So suppose if A is in R M by N. Okay, so M is bigger equal N. B is in Rn, and what do we want to do? We want to compute X such that Ax is equal to B. So can we solve this system of linear equations, over determined systems of linear equation, when the solution exists? Okay, so consider the first case. A is full column rank. What does that mean? It means that columns of A form a basis for the column space of A. So that is same as saying that it is full rank matrix. And the second thing that we say is that B is in column space of A. So if these two conditions are satisfied, then what does that mean? There exists a unique X in Rn such that Ax is equal to B. Correct? So there exists a unique X in Rn such that Ax is equal to B. So that means that the solution exists, and that solution is actually and the solution is actually unique solution. Okay, so in this particular case, this is what is happening. Another thing to observe here is that this A matrix is a tall matrix with full column rank. So we know that if A is full column rank matrix, then left inverse of A, if you compute, then that left inverse of A will give you some indication about what is the solution, right? You can choose the solution candidate from the left inverse of A, right? So that's what also we have seen. So here what we are going to do through QR decomposition is actually to build one such left inverse and use that left inverse to compute the solution. Okay, so that is what we are really going to do. So let us see how we can do this thing. Okay, so suppose A is the matrix. Okay, so this matrix A is like this. Now what am I going to do? You have more number of rows than columns, right? So what I am really going to do is that I am going to kind of transfer this matrix A into a matrix R. So now this matrix R is such that it is not uh, this thing. Okay, but this is like your M by M block. Okay, and so this matrix is entirely 0, and this matrix is also 0. And these are how many rows? These are M rows. Um, Sorry, these are N number of rows and N number of columns. So this is N by N square matrix. Okay, and this is 0. So if you take M is equal to 100 and N is equal to 10, for example, then you have 100 by 10 matrix, which looks like this. And you look at this 10 by 10 matrix. Okay, N by N. So 10 by 10 matrix you look at, and this 10 by 10 matrix is such that this is an upper triangular part. Okay, and all these rows, remaining 90 rows, all of them are 0, right? So this is basically a 0 block of the size 90 by. So suppose I convert my matrix A into an R which looks like this, then what happens? Okay, what really will happen? So that convergence happens by multiplication by a matrix Q. Okay, so Q transpose A, if that happens to be a matrix R which is almost upper triangular, right? So if that happens, what will happen to the entries here? All these entries, can you tell, in R with the conditions that I have, and Q orthogonal, if I am able to do this, what will happen to the diagonal entries of this submatrix? So I'll call this R hat, say, and this is 0. So R is basically equal to R hat 0. And R hat is N by N square upper triangular matrix. what will happen to the diagonal entries of R hat? All the diagonal entries of R hat, do you agree, will be non-zero? Because if one of the entries of R hat on the diagonal is 0, then the matrix R hat is going to be a smaller rank matrix, which is not possible because A and Q transpose, both of them are full rank matrices, right? So that cannot happen. So this diagonal entries of R hat are going to be all non-zero entries, and then you can use back substitution to actually find the solution X. Okay, so what we are going to do is basically as follows. So you have this matrix A and you have this first column, right? You have this first column. So what you will do, you will build one orthogonal matrix either through rotators or reflectors, you don't worry. Q1 transpose, we'll call it. What will happen, you will get this star and zeros, correct? And here whatever happens, I really don't care at this point of time. But the second column will be like this, right? Do you agree? Can I construct this Q1 transpose in this particular format? So if this is a matrix which is of the size m by n, if this is a matrix of the size m by n, what will be the Q1 transpose dimension? Like in which space Q1 transpose will belong to? In which space Q1 transpose will belong to? M by m. So using that m by m orthogonal matrix, I can make these how many entries? M minus 1 entries to 0, right? So that is what I have done. I can make this 0. Now I will multiply this by Q2 transpose and I'll make these entries 0. I'll make these entries 0 and so on and so forth. How many orthogonal matrices I'll require? Qn minus 1 transpose, and I'll get a matrix which is R hat here, right? So this will be basically R hat 0. And how does R hat look like? R hat looks like n by n matrix, which is Rn by n, all entries. This is how Rn hat looks like, right? So if you want, you can put n here to specify that it's this, correct? And now these are orthogonal matrices I can construct through the operations that we have just learned, either reflectors or rotators. And this will imply that Q transpose, so I'll multiply, I will call this Q transpose. So Q transpose into A is equal to R, which is nothing but R hat and 0. So if that is what you have, then you have Ax is equal to B, correct? That is the system of equations you want to solve. So I'll multiply by Q transpose Ax is equal to Q transpose B by this Q transpose. That means that I get R hat into 0 x is equal to Q transpose B. But what does that mean? I have this matrix which is upper triangular, and I have exactly these number of x1 up to xn, correct? X1 up to xn is equal to Q transpose B. And now what is happening? Using the backward substitution again. One can solve for x1, x2, xn. Correct? One can solve for x1, x2, xn. And your job is done, right? Your job is done. So that's how you will actually calculate. So you can write down A as QR and this R hat. Okay, so actually this R will not have this 0. It will just be a square matrix. Okay, so you should have corrected me. But this will be only a square matrix, right? Because the dimensions of Q transpose, what are the dimensions? N cross M and this is n cross n, so you'll get n by n, so square matrix. If you had completed the basis, then you would have got this rectangular matrix. Okay, so that's what has happened, and you know, this will give rise to a left inverse calculation also for A, right? So if this is A, that implies left inverse of A will be R inverse Q transpose. Correct? Left inverse of A, U, if you want to call it, will be R inverse Q transpose. Because then U into A, which is equal to R inverse Q transpose QR, will be equal to identity matrix. So that is your left inverse. Okay. So this is the left inverse. So this is the left inverse that you calculate using QR decomposition, and this actually is the solution candidate, right? And now you know, because of this condition that you started with for this rectangular system, that A is full column rank matrix and B belongs to the column space of A, because you know these things, there is a unique solution. So once you compute this solution, this is a unique solution that you have, right? So that's the way you can use QR decomposition to solve even the rectangular system of linear equations. Okay, so here we have demonstrated how you can calculate QR decomposition and use it to solve the rectangular systems of linear equations also. Okay, so
Sir,
yes.
sir, can you go back 2 slides once more? Sir, here, can you explain, like, you took dimension of Q transpose to be n by n, but while making the vector, we took the dimension to be m by n.
No, so okay, I made a little mistake in this. If you really want, I can show you here. Okay, so this is 100 by 10 matrix, right? A. So this matrix is 100 by 10 matrix, and now this 100 by 10 matrix, what will I do? This 100 by 10 matrix, I first construct one matrix Q that makes this, right? So even 100 by 10, I can take it to 100 by 3. So this 100 by 3, first operation gives me star and all zeros, right? So that is what will happen. Then there are two columns remaining here, right? How many columns are remaining here? Two columns are remaining here. Then what happens? So this is the first column of A1, right? Then A2, I choose this Q2. I choose this Q2 such that star star 0 0 0 happens. Okay, all these are 0. And now third column is here. So I get Q3 such that star 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 and 0 0 0 will happen. Correct, no? Is that okay?
Yes, sir.
Yeah, that's the operation that I have done. That's all. Okay. Is that fine, Kshitish?
Yes, sir.
Yeah, and now you see this is the upper triangular matrix that is really of interest to us. Okay, so that upper triangular matrix is really a matrix which will help us do these things. That's fine.
Yes, sir.
Yeah. So this matrix I called R hat, and this matrix that you see here is that zero matrix, and this is what we will be doing. Okay, and when you multiply x to this, then you will multiply x to this, so x will be only x1 x2 x3, right? In this particular case, x will be x1 x2 x3. So x1 x2 x3 you can calculate using back substitution. X1 into first column, x2 into second, and x3 into third column, right? That's what you will do. So back substitution will tell me first x3, then x2, then x1. You calculate and your job is done. That's all. Is that okay? So what
Yes,
we
sir.
have, yeah. So what we have done is we are looking at the system of equations Ax is equal to B. That is what we are looking at. And what did we do? The first thing that we do is the solution to this system of linear equations. Okay, solution to this system of linear equations. The second condition is computation of this solution. Okay, the second thing that we were focusing on was computation of this solution. Okay, so this thing was done, this thing is done. So in this thing, we looked at LU and QR. Okay, so LU was equal to Gaussian, and we looked at this QR decomposition also, and we learnt about the concept of left and right inverse and invertibility and so on and so forth, right? So there are several things. I think we talked about gram matrices also when we showed about this left inverse and full column rank conditions, equivalence, and so on. So, right? So we talked of gram matrices also. So these were the things that we understood. These were the concepts that we developed in order to do the computation of this solution. And the third thing that we really want to look at is the sensitivity of a solution. Okay, sensitivity analysis. That's what we want to do. Okay, so why this sensitivity analysis is important? Okay, so that is something that we will first try to understand, and once we understand this, then we will start looking at how we really quantify this sensitivity analysis, and we see what we are really going to do. Okay, so why these things are really important, we'll understand that, and once we understand that, then we go into the details, and then we see what is really happening. So sensitivity analysis, we want to start now. So this is the last part about the system of equations Ax is equal to b that we want to do. So while we are going to talk about sensitivity analysis, there are several things that will be developed along the way. Okay, so in this particular thing of sensitivity analysis, no, sensitivity analysis and backward stability are not same. They are actually different things. And what we want is we want sensitivity as well as backward stability together to get good numerical results. So we are not going to talk of backward stability here in this particular course, but we are going to talk of sensitivity analysis for sure. Okay, so all these algorithms that I am discussing in the class, especially the QR decomposition that I discussed, then how to compute this QR decomposition and all. So these type of algorithms we'll consider they are already backward stable. Okay, we'll already consider that they are backward stable. So backward stability is assumed. We will not worry about backward stability. So while we are doing this sensitivity analysis, in order to completely understand how you will do sensitivity analysis, several things are required. So the first thing that we will do is vector matrix norms. Okay, so we will understand these vector matrix norms. Then we will understand this magnification concepts. Okay, magnification concepts, which is maximum magnification and minimum magnification kind of thing by the matrix. Okay. So these are the geometrical meanings. So once we understand these geometrical meanings of maximum magnification, minimum magnification, then we'll define something which is called as condition number of matrix. Once we define what is condition number of matrix, then using this condition number, we will derive several results. We'll derive several results for sensitivity analysis of Ax is equal to b. Okay, so that's what we will do. Then we will actually do something which is very important for us, singular value decomposition. And once singular value decomposition is done, then what we are going to do, so this is for square systems. Okay, so Ax is equal to b, this will be done for square systems. Okay, then we will do SVD, then we will do least squares problem. Okay, then we will do least squares problem, and then we will do sensitivity analysis of least squares problem using singular value decomposition. Okay, so that is the flow. That is what we are really going to do. So now, first things first, why do we really want to talk of this sensitivity analysis? So I had earlier said this thing, but let us try to understand this thing once more by a numerical example. Okay, so let me take a very interesting and special numerical example. So let us 2 by 2. Okay, so the example is as follows. Consider the matrix A. So I think similar example I had already taken. Okay, I think 10, 9, 9, 8. That was the example I had taken. But to dramatize the effect, I am taking this particular example. Okay, so let us consider A to be equal to this. Then clearly you can see A inverse. I will just write down. You can verify whether A inverse is really this or not. Okay. I am writing it for your convenience, but you can check that this indeed is A inverse. Okay, so this is the matrix that you get. A inverse. Okay. Now, can you tell me the solution to this system of linear equations? Compute x such that ax is equal to b, where b is actually this. Can you tell me what is the solution to this system of linear equations? So I already gave you A inverse, right? Use that A inverse, and using the A inverse, can you just tell me what is the solution?
1, 1.
1, 1, correct. So x is actually equal to 1, 1. Okay, this is one calculation. Compute y such that ay is equal to this. Can you compute what is y? And before even you start computing y, can you tell what do you expect? What have I done? What I have done is that I am given matrices A and B typically, right? So this is the matrix A that is given to me. This is the vector B that has been given to me. Now, what has really happened is that somebody was measuring the data stored in vector B. So somebody who measured data gave me this 1999, 1997. The same data could be measured by another equipment. Okay, but because equipment changed, the measurements changed slightly because of the noise or the inaccuracies that might have come out because of change of the equipment, and those inaccuracies were like this. So the data in B is ever so slightly changed. Data in A is not at all changed, but data in B is ever so slightly changed. For this ever so slight change in data in B, what do you expect to see in Y? Do you think y will be close to x? Do you think y will be close to x? Just see and tell what is happening. A inverse is still there with you. You still have computation of A inverse. That will not change because matrix A has not changed. So what will be y here?
One 1.01 and 0.99.
1.01 and 0.99. So I made a change which was very small. So here roughly like some change I made, and that change reflected in a slight change in vector y from x. This is reasonable, right? This is something that you would expect to see, that I make some small changes in the data, then the x vector changes ever so slightly, right? X goes from 1, 1 to 1.01 and 0.99. That's okay. That is what you typically expect to see. But now I will ask you to solve this. Okay, so compute z. Okay, compute z such that az is equal to, what was the vector here? 199. Okay, so 1998.99 and 1, what was the vector here? 1997. Okay, ever so slight change, right? Ever so slight change in the data vector B. What is z now? Actually calculate, you calculate this. Everybody, I want everybody, all of 130 who are attending today, I want you to calculate Z. You multiply A inverse to this right hand side B and you actually calculate this value of Z for yourself. Take 1 minute, I don't mind waiting, but I want you to do it to make sure that you understand what is happening.
Sir, could you show the matrix B?
Sir,
Huh?
20.97 and minus 18.9.
20.97
and minus 18.99.
minus 19
18, sir, 18.
minus 18.
0.99.
So what happened here? What happened here? You ever so slightly changed. Oh, why you are getting 999, Kshitish? I think
No,
this
sir.
answer is
I
correct.
made another point.
Yeah, I think this is correct. 20.97 and minus 18.90. I think this is correct answer because I also got this answer. So now you see what? Here in this particular case too, you saw that you changed the right hand side B vector, the data in B ever so slightly. The change in Y, the change in X, which was Y, was not too far away from X, right? The change in X, which is equal to Y, is not too far away. But here also, you change the right hand side ever so slightly. You change this right hand side ever so slightly. The change in X, which is now Z, you see it is like unacceptable now. Z is going, like Z is too far away from X. It is unacceptably far away from X now in this particular case. You see this? So what is the observation here? Observation is the following. Small changes. Okay, so small changes in B may lead to large changes in X. And this is something, this is undesirable, right? You don't want that to happen. If this is happening, then you are in trouble, right? So why such an analysis is important, right? This is not only mathematical fantasy. Okay, so we know, now pay attention. This is for you. Okay, so what is this? Suppose a similar problem. Okay, so similar problem. Similar problem is you have a tall matrix is equal to B. And this matrix is coming out. So this is a regressor matrix. So what is regressor matrix? This matrix corresponds to the data for which attributes are given to you, right? You are solving the problem y is equal to alpha 0 plus alpha 1 x1 plus so on and so forth plus alpha n xn plus epsilon. That is the regression problem, multiple regression problem that you are trying to solve. So x1, x2, xn, these are stored here, right? And this is the column of all ones. So this is your matrix A. Then this vector X is basically the vector of parameters alpha 1 up to alpha n. And what is the right hand side? The right hand side is the measurements Y. The right hand side is measurements Y, and you are saying that while you measure, you are worried that there is some error that goes into the measurements. That error is epsilon. So that error is really small, but these measurements here, y1, y2 up to ym, which is the number of data points that you have, ym, which is nothing but the vector b, it is prone to error. There are certain errors, there are certain noise terms that will get added to this. So this y maybe actually y1 tilde, y2 tilde, yn tilde, some changed version. So this y may be something like this, error getting added to this. And if that is what is really happening, then you see when you actually calculate the solution x, meaning the true value of the parameter was, for example, 1, 1. Now what is happening? The true value of the parameter is going suddenly to 20 and minus 18, because there was a small perturbation in the b values, because there is small perturbation in these y values, and that perturbation is also not unrealistic. It is coming because of the assumption that we have in the model. That is the measurement error in y, that is always going to be present. And that small measurement error in y, if it is taking the true value of y to a small perturbed value y plus delta y, which I am representing by y1 tilde, y2 tilde up to ym tilde, then this vector b tilde is actually this vector b tilde, right? The right hand side ever so slightly perturbed from the true value that you had here. And if this happens, then you see how much is the change in the parameter vector that you find out. So this is the estimate of the parameter, right? And you see this estimate of the parameter goes too far away from the true value of the parameter. Do you want to use such an estimate in subsequent analysis? So these are the values of estimators that you get, and these are the estimates. Will you use these estimates? Obviously, these estimates will affect everything that you are going to do subsequently. That's right, right? So you want to know how much is the effect, that you are inducing, how much is the variability in the estimates of the parameter that you are estimating because of small perturbations in matrices A and B. And here I am only looking at perturbations in B. I have not even perturbed A, but I can perturb A also, because A is also some data that I am collecting from the measurements. So that data is also prone to the measurement error. Then I have problem with A also. Then I'm not really working with A, but I'm working with A plus delta A. And I'm not really working with B, but I'm working with B plus delta B. Then how is the true value of the parameters X are getting affected? Because I am going to get X plus delta X. And what is the hope? The hope is that this delta X is not really too big. That is what the sensitivity analysis is going to tell us. So what is sensitivity analysis going to tell us? Sensitivity analysis is going to tell us how much this X will vary, how much is the maximum variation in the parameter or in the solution X that you obtain if this is the perturbation that you give to A and B. Okay, so small, large, these are the terms that we will start quantifying. Okay, so this small, large, they are the terms that we will start quantifying through a concept which is called as norm. So that's why we first need to understand what are the matrix and vector norms. So once you understand that, then you will be able to quantify these perturbations. Okay, then we will see through the action of A what is the maximum and minimum magnification. Then we'll define something which is called as condition number, and then we will give some bounds. Okay, so derive several results. What we are really going to do, we are going to give some bounds, and those bounds are going to tell us how much is the perturbation that you can expect in the solution X because of inaccuracies in A and B matrices. So do you understand what we are going to do in sensitivity analysis? Do you understand what we are going to do? And this is the toy example that I showed you. Through that toy example, I'm trying to illustrate why asking this question and why doing such an analysis is really very important. And this regression problem is something that will really be the place where we want to do this analysis. So this regression problem will be least squares problem. So that sensitivity analysis has to wait until we introduce SVD. And once we do that, then using this type of sensitivity analysis, we'll learn several interesting problems in AIML, something like principal component regression. why principal component regression is necessary, why do you do that, and by doing principal component regression, what are you achieving? These are the type of things that we will study. Okay, so this sensitivity analysis eventually will tell us what is really happening and why you need principal component regression. And while understanding the sensitivity analysis, you will develop several useful concepts like SVD, least squares regression, and so on and so forth, condition number. And then we will generalize this to least squares, and then through SVD, we can take a different direction also of principal component analysis, low rank approximation of matrices, and several other applications using that, right? So this is what we are going to do. So first we'll do SVD, we will understand least squares problem, we'll understand sensitivity, and then again you come back to SVD and you take a different route of understanding these low rank approximations. Then again from SVD you take another route, you understand eigenvalue, eigenvector decompositions, and several applications of that also in AI. Okay, so this is what we are going to do. So first we want to do the sensitivity analysis. Like I said, putting everything in context, we were looking at Ax is equal to B. We characterized the solution. We characterized couple of algorithms to compute this solution. And now we are going to do sensitivity analysis. Are things in perspective now? Do you understand why we did few things and why we are going to do subsequently few things? Any comments here? Any doubts? Any additions to what we have done?
Sir, if you can go to the next slide. Yes, sir. Sir, in this, the major problem is that the numbers in A are very huge, right, as compared to the perturbation. That's why the result is being magnified, the error in the result. So
not really, but these numbers have something to do.
Okay.
But those numbers being really large is not the only reason. I can take the same example 10, 9, 9, 8. I will take the same example and I will still be able to construct few things, few perturbations, and you will see that the change is very significant. Okay. Even if the numbers are small, I can do that. But yeah, so it is not only to do with the entries of the matrix. It is to do with the condition number of A also. So we are going to arrive at that. Any other observation?
Sir, one more observation that on the right hand side, on the labels that we see that all of them are perturbed. I mean, here we have two and both of them are perturbed. But say, for example, if we have 100 observations, 100 tuples, and if we have like a few perturbed, will we expect to see the same kind of disruption?
Depends on A. So all of those things will depend on how A is, how the matrix A affects really. Okay, these things. So that's what we are going to learn. So first we see that something like this is plausible. And now the second question that we want to answer is that why is such a thing happening? Okay, why is such a thing happening? So what are the type of matrices A which will induce such a thing? What are the type of matrices A which will not induce such a thing? And that is something that we will like to understand. So that is what we are going to understand in sensitivity analysis. So the question you are asking me that some of the entries of B are perturbed, some other entries are not perturbed, then will you still see an effect as magnified as this Z? That actually depends on matrix A as well. Okay, so here the things are to do with matrix A. We'll see how those A matrices really play a role. Okay, so we'll see that. So in general, the answer to the question is I really don't know because it is decided by matrix A.
I think in this example also, if we take perturbation and say suppose we take 19901 and 1997, still we are getting some significant change.
Yeah, you will get sometimes, you will not get sometimes. So whether it happens or not depends on how A acts on some vectors. Okay, so we'll see what I mean by that. But in general, the answer is we'll have to check. I don't know. Any other observation? Okay, so in first place, do you appreciate the need to study sensitivity analysis?
Yes, sir.
Yeah, the need to learn sensitivity analysis. So now you think of this situation. We are only in linear algebra and we are only looking at linear models in AI and ML, like regression model, the simplest possible model. And that simplest possible model also may present challenges as big as this when you have introduced some perturbations, right? So now you think of it that you are using extremely non-linear models that you are having and all those type of things, and you change the data ever so slightly, what would really happen? So you would need to do something equivalent of sensitivity analysis for those highly non-linear models also, right? In order to understand whether the problem is well posed or not, so to speak. So do you understand? This is only for a very simple problem. This is happening. And you might have highly nonlinear models. You have built a huge deep network. And now, suddenly all the weights on the edges, those weights are like your parameter vector X or alpha. They're going to suddenly change if you ever so slightly change the data. Would something like this be desirable? I don't know. We have to investigate. Would something like this happen? Possibly something like this might happen. That also we don't know. So this is the type of study you may want to undertake. So what are the types of tools and techniques that you need at your disposal to do this type of analysis is something that I'm going to illustrate here on a very simple problem, which is a linear problem, Ax is equal to. Okay. So as everywhere, as in all science and engineering branches, the simplest thing are always done in the classroom. So this is the simplest thing, a linear model. I'm going to do that in classroom. All of you who are engineers would have seen that you all have a huge big course in linear systems theory, right? And you are left hanging when the real life nonlinear system comes your way. So exactly same thing is going to happen here also. I'm going to do this analysis for linear systems, Ax is equal to B, and I'm going to leave this question hanging to you, saying that, okay, you see for nonlinear models, you'll have to do something similar. You need sensitivity analysis in place for nonlinear models. How to do it, I'm not going to say. It will be case by case in your own application, in your own area of research. You will try to do such things. Okay. So I hope you appreciate the need of sensitivity analysis, and I'm going to demonstrate it for a very simple class of models that you will encounter, linear models. Okay. So that's what we are going to do in few of the classes from here on. Okay. So where are we going to start in sensitivity analysis? As I said, in sensitivity analysis, we are going to start with vector and matrix norms. And why are we going to start with vector and matrix norms? Is that I am talking of things like small changes, large changes. So these small changes, large changes, somehow I have to quantify. And that quantification will come through norms. So that is why I need vector norms and matrix norms to start with. Okay. So that's what we will start. So far, any doubt, any question, any doubt so far? Any comment? Okay. In that case, I think today we'll stop here. I have some other work to attend to, unfortunately. So I will not be able to take class until 1 o'clock fully. So we'll stop here. In the next week, we'll start with this sensitivity analysis. Okay. So in Wednesday and Thursday's class, we'll try to cover this vector matrix norms and this maximum and minimum magnification concepts. Okay. So this maximum and minimum magnification concept basically is what you say is the geometrical interpretation of matrix norms. Okay, so what matrix norms do geometrically, that will be understood through this magnification concepts. So that is what we will try to cover in next week, Wednesday, Thursday, and Friday we'll have exam, and then the week following next week we'll continue our discussion to complete this sensitivity analysis. So thank you. Today we'll stop here.